Hi everyone, and welcome to Level 1 Energy Advisor Training here at GreenFoot. We are so excited that you've decided to join our team, and we look forward to growing and learning as we move forward together. Over the course of the next few videos, you're going to learn the basic technical information surrounding some building science, renewable technologies, energy conservation, and HVAC systems. All of this so you'll be able to offer practical and helpful energy advice as you customize a plan with our clients. In this section of the video, you will learn the basics of energy, and you will also learn the 3 types of heat transfer so that when you're talking with customers, you'll be able to explain how our products and services can lower their demands of energy during their heating and cooling seasons. Take a look at this.
Energy is what makes things go, run, or happen. So let's make something happen. Say with this big box of water. See, when we filled this box, we lifted the water up here. And when we did, we gave it some energy. Think about it. You have to work to lift a bucket of water. So when you lift it, the energy of lifting is stored up here. I'll prove it to you. When we open this valve, water flows downhill and runs this little propeller. The propeller spins and runs a little generator which makes a small amount of electricity. It runs through this wire and makes this needle move. Some of our electricity is made by falling water at huge dams that have huge propellers. When energy is stored, we call it potential energy. It has the potential to do something. When it's moving, we call it kinetic energy. Kinetic means moving. Now this setup converts the potential energy that we put into the water by lifting it to a form of kinetic energy, the energy of the flow. And the flowing water makes electrical energy. Kinetic energy was converted to electrical energy. Energy was changed from one form to another. Not bad. You know, I'm kind of out of energy.
Energy can be defined as the ability to do work. And really, there are 2 different kinds of energy. One is potential energy or stored energy, which can be found within chemicals, for example, or even within atoms, within our planets and our gravitational system, and can be stored within elastics as well. A good example of this would be gasoline. Gasoline is burned in an engine, so when the chemical bond that holds the atoms together is ripped apart, large amounts of energy are released. So it was stored in the chemical, and that's basically used to do work, mechanical work, in order to run a vehicle, for example. Heat belongs to the second class of energy, which is called kinetic energy. Kinetic is a Greek word which means motion, to move. You may know someone that has studied kinesiology, or the study of human movement. And thermal energy, or heat, is the movement of particles. So particles are always moving, and they're constantly colliding into each other, and those collisions actually generate heat. There are other types of kinetic energy, like mechanical energy, electrical energy, and magnetic energy. And those are all used. And whenever you transfer from one form to another, whenever you switch energy forms, there's always heat giving off. Let's think of a practical example. If you've ever been to an amusement park, or you've been on a roller coaster, you've experienced potential energy, as well as kinetic energy. Let's think about it. You get on the roller coaster, and as you're going to the top, the electrical energy used to power the electrical motors is putting you at a higher level than you were before. And that's storing up some energy. And then you don't need to use electricity anymore because you have stored all of that electrical energy into the carts. So they get to the top and down you go. So now it's the energy of motion. So the potential energy is now transferred to kinetic energy as you move down the steep slides and move all around the roller coaster ride. When you're thinking of heat, consider thinking about it like a particle. Here's a good example. Have you ever been to a movie theater where someone comes in and sits down and they have strong perfume or cologne on? Well, the people immediately around them are the first ones to smell it. And that's because those particles that are bouncing around through Brownian motion, it's called, are bouncing all around, and they're hitting other air and perfume or cologne particles, and it spreads out. And it moves from an area of really high concentration to an area of really low concentration. So heat is much like that. And at a heat source, it often moves from an area of high concentration to an area of low. Consider a home here in the winter. On the inside of the home, it's around 20 degrees, and on the outside, it could be minus 20, for example. Well, the area of high concentration for us is inside the home. There's lots of heat in there, and it will have a tendency always to move out to an area of low concentration. And so we're going to look at how heat transfers that way, the three modes, and how some of our products and services can really help in reducing that movement of heat from the inside of the home to the outside. So we know heat moves from an area of high concentration to low concentration, but how fast? This really matters when it comes to heating and cooling your home. The factor that affects this the most would be the temperature differential, or it's referred to as the delta T. So if you have big temperature differentials, then the heat transfer rate will go up. It'll be harder to heat a home if it's really, really cold outside, because your heat rate of change would be going out really fast. However, in the spring or fall, when the temperatures are around the same, you don't really have the same heating and cooling load because the rate of heat transfer is really close to nil. So today we're going to talk about the three types or modes of heat transfer: conduction, convection, and radiation. Now, we're going to have to head back to high school just to kind of get some basic understanding of particles and particle motion. See, everything is made up of atoms, and atoms are constantly in motion. Particles are bumping into each other all the time. And these bumps, these collisions, generate heat. So really, everything generates a little bit of heat. If you add energy to a system and you make those collisions happen faster, then you have more heat. Consider this, for example. This is a heating element. And as I turn it up, as I increase the amount of electricity that moves through the filament or through this burner, I actually cause those particles to bump into each other a lot faster and faster until they get actually really, really hot. And that's called conduction. Conduction is a heat transfer when touching. Further, we can add a pot to this, and as the heat is moving from an area of high concentration, the burner, to low concentration, the pot, it'll heat the pot up. It'll move those particles around faster and faster. The temperature will increase. Take a look at this formula. Here it is. C equals A multiplied by your delta T divided by R. In this formula, C represents your conduction. A represents your area, and the delta T, of course, we talked about is your temperature differential, how much the temperature is different. R, in this case, is your thermal resistance, and are often referred to as the R value. So let's take this formula and look at it. We can break it up into kind of proportional statements. So from this formula, we can see that the conduction rate is proportional to area. In other words, when your area goes up, your conduction rate goes up. Well, we can also say that the C is proportional to the delta T. So if the change in temperature goes up, then so does your conduction rate. Now look at this one. This formula says that C, or conduction rate, is inversely proportional to your R value. And what this means is that as your R value goes up, your conduction rate goes down. So in other words, the bigger the R value, the less energy will be transferred, the less conduction can happen. So now we can see why insulation is so important. It actually slows the rate of conduction, so that if you spray foam or add insulation to a wall, that the R value, the insulating factor, goes up, the conduction rate goes down. That heat has trouble moving from an area of high concentration to low. The movement of heat through a fluid, that is any liquid or gas, is called convection. And convection currents occur naturally in the world around us all the time. In fact, it's the main way that heat is dissipated through our globe. Think about the equator and how the heat is concentrated there. It's an area of high concentration. Well, convection currents, that heat is then pushed into the air and that is rolled out to the poles. And that's how heat is dissipated across our planet. Another practical example could be just going to the beach in the summer. You have the water surface meeting the land surface, and those two surfaces absorb heat from the sun in very different ways. In fact, the water absorbs heat slowly, whereas the land absorbs heat from the sun quickly. And so because of that, now we talk about convection. Convection heats the air above those two surfaces. Well, it's heating the air above the land a lot faster. And so those particles move and bounce into each other much faster. They spread out and they actually become less dense. And that's what people refer to when they say heat rises. It's not heat that rises, it is warm air or hot air that rises because it becomes less dense. It moves up in the column and the colder air moves off of the water onto the land. And so if you're standing in a nice warm day at the edge of the ocean, you'll often have a breeze of wind coming at you. That's a convection current. Likewise, in the evening, you could expect that to be in reverse, where the hotter body of water in the cooler land after the sun goes down sets up a convection current where the warm air, the less dense air rises above the water, and the cooler air off the land fills its place. And so you might expect a breeze to go at your back if you're looking out at the water. And so those are just natural examples of convection currents. And although convection currents occur naturally, even within homes, it's often desired to have that happen much faster. For example, in a home, you have a furnace which generates heat, and you want that heat transported to the upper floors or the lower floors or just dispersed around your home. We often use mechanical means, and that's called forced convection when we do that. So you would have a blower on top of your furnace, which after the air is heated, it is then pushed around to the various places of the home. So that's called forced convection. And if you take a look at this formula, C equals F multiplied by your change in temperature, again, we can look at it and pull it out. It's clear C stands for convection in this case, F is for your flow, and delta T for the temperature differential or the change in temperature. So we can bust this apart and you can see that the convection is proportional to the flow. In other words, if the flow goes up, if the convection currents cycle faster, then the conduction will be faster as well. And it's also C is proportional to the change in temperature. So if you have a bigger temperature differential, you're going to have a faster convection. So now you can see why it'd be really important for us to understand the basics of pressure now in building science. It's just practically speaking, how does this work and what should we be looking for when we're heating and cooling air? Think about the stack effect. The stack effect is magnified with taller buildings, but let's just consider a typical two-story home. When it's cold outside and you heat the air inside, that air becomes less dense and it rises to the top floor. And so as the less dense air rises, it creates this higher pressure on the top of the building and a lower pressure on the bottom. And so what that leads to is air escaping through cracks, and all buildings are not airtight, so it's escaping through cracks and crevices at the top. And that is also leading to an infiltration on the bottom, that the high pressure pushes the air out the top, but also creates this vacuum and sucks the air in, much like a straw, on the bottom floors and through the cracks and the crevices of the buildings. So imagine a really tall building where that pressure gets really high at the top and really low at the bottom, and you have a lot of air circulation from the internal envelope to the external. So that's called the stack effect. It's exactly reversed when we cool the air in our home. So imagine a hot summer's day and we're cooling the air, and those particles are moving around less and they're packed in tighter and they're dropping down to the bottom floors of a building, and that's creating a high pressure of air at the bottom and a low pressure air on the top. And so we have the same sort of thing. As the high pressure pushes the air out of the bottom floors, it actually sucks in the air like a reverse straw through the top floors, and then we have heat from the outside coming inside. And so that is a general overview of the stack effect. And hopefully now you could also see that the combustion and ventilation effects would alter the pressures in the home just based on venting and ventilation issues. So that just adds a whole another factor, another layer of turbulence to the movement of air through the home. In order to speak about thermal radiation, we first need to understand a little bit about the electromagnetic spectrum. Take a look at this. Here's the electromagnetic spectrum, and this really looks at the different forms of light and their wavelengths. So we actually exist, and we can see in the visible light section, if you can see right here. These are all the colors of the spectrum that our eyes are able to see. If you drop below that and you get a bigger waveform, a bigger period it's called, you're into the infrared radiation. We can't see these waves, but you can certainly feel them. Going backwards into bigger waves, you have microwaves and radio waves. Moving forward from our visible light spectrum, you can see ultraviolet light. That's the light, the spectrum from the sun. Of course, the sun would have all of these, but it's most intense there, and it gets a little shorter wavelengths, which means that they penetrate a little bit deeper. And that's why we can burn our skin if we're out too long in ultraviolet light. X-rays then can penetrate even further into objects, and gamma rays, which are the highest frequency waves, which penetrate the deepest into substances. So there's the electromagnetic spectrum. Have you ever been to Costco in the winter, or a rink where they shine this kind of red-looking light at you and you're warm? But as soon as you step out of its path, you're back to the same temperature? Well, that is a great example of thermal radiation, that the emitting source, which has a high concentration of heat, emits those light waves, and they hit the colder source and heat it up. We go back to our example of the beach. This is a perfect example of that. And it also depends on the surface. So the surface of the water is shiny, and the surface of the land is not. And so it has trees and sand, and so the ultraviolet radiation and the infrared radiation and all of the different types of light spectrum hit those two different surfaces, and where one is reflective and reflects that back into space, the other one is absorbs it, and so then it warms these bodies up. This is the reason we don't wear black shirts in the middle of summer when we're working outside. It absorbs all that energy, keeps us hot. It's also the reason that when at night you warm yourself by a campfire, you can put your hands out, and although nothing is touching, the air isn't moving over like convection, it is the radiation that warms your skin. Applied to a house, and an alternative to conventional convection type heating, you have radiant floor heating. These types of heating systems use radiant energy from the source of the fluid moving through the pipes to heat the immediate area above that pipe. So the heat actually does not create this warm pockets of air that are moving around. It's actually you just be there and receive the heat through those radiation. In a typical home, less than 10% of heat loss is due to radiation through windows. So that leaves conduction and convection as our main culprits for heat loss in any home in our area. So just to summarize, when it comes to heat transfer, there are three modes of heat transfer: conduction, which is touching, molecules moving around and emitting energy through that. That's touching. We have convection, and that is the movement of energy through any fluid, gas or liquid. And then we have radiation, which is the movement of heat through really light, an electromagnetic spectrum. Well, I hope you can see how an understanding of heat and energy can better prepare you to offer our services and products to the customers who have a lot of questions about what we do and the science behind it.